Hello and welcome to the presentation of project HyTruck, HyTruck Austria. My name is Alessandro Ferrara and I'm a university assistant here at the Institute of Mechanical Mechatronics of TU Wien. HyTruck is an FFG project which is coordinated by AVL but involves a larger consortium of partners, and the end goal is to develop and validate a heavy-duty fuel cell powertrain to fulfill requirements regarding power, efficiency, reliability, and lifetime for heavy-duty applications. Here, we at TU Wien are responsible for the development of innovative control strategies, and in particular, we want to investigate the use of predictive driving information in energy management strategies to assess potential improvements in hydrogen consumption and component life. When it comes to the electrification of road freight transport, there are essentially two possibilities: fuel cell electric vehicles and battery electric vehicles. Whereas for the market of passenger cars, battery electric vehicles are dominating the scene, for heavy-duty applications, fuel cells have higher potential thanks to their higher energy density and faster refueling times. However, three main barriers have to be still overcome, which are high cost, low lifetime, and missing hydrogen infrastructure. Any fuel cell powertrain looks like this. There is a fuel cell and a battery system which provide energy to an electric motor which drives the vehicle. Because there are two power sources, we need an energy management system to distribute the load between the two systems. This task is usually called power split. When it comes to the energy management of fuel cell vehicles, the targets are maximization of hydrogen economy, meaning that we want to operate the fuel cell in a high efficiency region, mitigation of fuel cell degradation, meaning that we want to avoid frequent shutdowns, limit low and high power operation and transient loads, and mitigation of battery degradation, which we can obtain by keeping the charge within prescribed levels, avoiding critical temperatures, and limiting high C rates. When we satisfy these control solutions, we can limit the critical conditions such as reactant starvation, high temperatures, dehydration, and flooding in fuel cell, for example, which severely affect the lifetime of the system. Because we want to develop a predictive energy management scheme, we need to use predictive driving information. And here we have two possibilities, either long-term information or short-term one. The long-term information, for example, is the one provided by a navigation system when a new destination is inserted. So from that we can obtain the elevation profile over the entire route, as long as, for example, speed limits. For the short-term information, we need an onboard and online prediction systems which looks at traffic speed, road conditions, road slope and curvature to forecast the speed of the vehicle in the next kilometers. The adaptive and predictive energy management system we developed within the project HyTruck is divided into two control stages: route planning calculation and onboard control. During the route planning calculation, when a new destination is inserted, the navigation system provides a forecast of the route speed and elevation, and through a vehicle model, we convert this information to a forecast of the electric load, which is then used for the predictive optimization of the energy management of the vehicle. The result of this optimization is stored as a predictive SOC reference for the entire route, which is then used in the onboard control stage by an adaptive energy management strategy for real-time vehicle control. The predictive SOC reference is really important when it comes to mountain roads, for example. Here it is important that before a long uphill road, the battery is fully charged so that the charge can be then later on be kept within safe levels, and also the vehicle doesn't need to stop for recharging the battery. What you can also see here is that at the top of the mountain, the charge is kept low because there is an upcoming downhill road, which means high regenerative braking, and therefore we want to you maximize the absorption of regenerative braking, which in turn means having a higher hydrogen economy. The adaptive and predictive energy management strategy is based on a model predictive control, which minimizes a constrained objective function to define the fuel cell set point, and is based on instantaneous and successive linearization of a model which is otherwise nonlinear. The control strategy is adaptive to battery temperature, meaning that the operation criteria change depending on the temperature. For example, at low temperatures, we favor the optimal fuel cell operation, whereas at high temperatures, we limit the battery usage to allow the cool down of the system. We achieve this by defining an adaptive multi-objective cost function. And here the peculiar thing is that the weights of the cost function are depending on the battery temperature. The cost finds the trade-off between four terms: SOC reference tracking, hydrogen economy, ohmic losses, and fuel cell transients. And of course, the cost is minimized over a predictive horizon, and this is where the short-term driving information comes into play. The vehicle simulations consider a simplified and fast model in Simulink for the energy management design, whereas for the validation of the results, we consider as a real vehicle a more sophisticated and complex model in AVL Cruise-M. To obtain a robust design, we consider an extensive real-world driving scenarios framework based on logged speed and elevation of trucks operating in Central Europe. So now I'm going to show you a comparison between two energy management strategies: our state-of-the-art adaptive MPC with predictive SOC reference, and a non-sophisticated solution, which is a non-adaptive rule-based control with a constant SOC reference. Here you can see the speed and elevation of the vehicle in green, and also a snapshot of the road where this data was actually recorded. Then in blue we have the rule-based control strategy, and in orange the MPC. So here you have the simulation results of battery power, fuel cell power, SOC, and battery temperature. If we look at the overall results, we can definitely observe an improvement thanks to the MPC, of around 5% in terms of hydrogen consumption, but also an improvement in terms of fuel cell transients and high fuel cell power operation. For example, here you can see that the MPC stays away from the high fuel cell power because it's both inefficient and highly degrading for fuel cell life. Then we can observe a much better SOC control for the MPC, which means that the actual SOC in solid line, it's closer to the SOC reference in dashed line compared to the rule-based case, as it is also confirmed by the maximum deviation here. Lastly, we have the battery temperature, and here for the rule-based strategy you can observe a peak of temperature which reaches around 50 Celsius a degree, and this is effectively avoided by the adaptive MPC strategy. The same results are confirmed here for flat road, as you can see, and without looking into details at the number, we can just say that the performance improvements are retained, meaning that the control scheme we developed is not only good for extreme cases, as the one we saw before, but also for normal operation of the vehicle. In the end, we developed an adaptive control strategy and a predictive SOC reference generation method, which we combined together to obtain a reduced operating cost of the vehicle by reducing the hydrogen consumption, extended fuel cell lifetime by reducing the fuel cell transients and high fuel cell power operation, and improved vehicle performance and extended battery life by having a better SOC and battery temperature control. The energy management team involved in Project HyTruck from TU Wien consists of me and my colleague Said Zendegan for the technical level, and from Professor Jakobek and Nametner on the supervision level. I'm looking forward to receiving your questions via email, and I want to thank you for your attention and wish you a nice day.